Blended Podcasts. Brought to you by Blended Audio.
Hubby, welcome back.
Hey, that was scary.
We are back. What's up? Welcome to episode 10 of Talos Talks Shit. This is an immediate continuation of episode 9. We are looking at Google DeepMind, a company that wants to solve intelligence and use that to solve every other problem in the universe.
Actually, the universe.
Maybe
You're gonna
even
say the world, but like actually the universe.
Yeah, maybe even solve the universe and falsify the simulation. But
42.
42. Maybe. 1.618, dude.
Yeah. How funny would it be if it was like actually 43 or something? It's like
So close,
one
dude.
off.
Yeah, so we spent the last episode looking at AlphaZero as a continuation from AlphaGo, a way for researchers to take AI and make it more adaptable, more intelligent, really. It's, as you can probably see at every intersection in this podcast, intelligence and adaptability are super interlinked, and that's really the big prize is not super capability at one task, but ability for these AIs to do various tasks based on just an expansion in data set.
Yeah.
So once DeepMind had figured out AlphaZero and Go and Shoji and chess and whatever, they decided to tackle a problem in the universe, quite a fundamental problem in the universe.
Quite an important one.
Yeah, it's going to have huge ramifications for health sciences, and this is AlphaFold. And AlphaFold simply predicts a 3D structure of a protein based only on its genetic sequence.
Yeah.
So, a bit of background on that. We have progressed quite far in our genetic sequencing knowledge of the human race. We sequenced the genome in the late 90s, and since then, genetic sequencing capabilities have dropped in cost exponentially. So I think it was about $1 billion to get the first human genome sequenced.
Oh my
And
god,
you
that's
can
a lot
do
of money.
that's a lot of money, eh?
Yeah.
And you can do the same extent of sequencing for I think like $30-40 nowadays. It has dropped so exponentially.
Yeah, it's 5 orders of magnitude. right?
Exactly, yeah.
Wow.
So that's opened up huge doors for human biological understanding. But protein chains...
So it's more than 5. It's like a billion's what, like 9 zeros?
Yeah, billions, 9 zeros.
So it's like 8.
8 orders of magnitude.
Wow.
Yeah, it's dropped by 8 to 10 orders of magnitude in terms of cost. And which, as we know, anytime a cost drops for any new technology, that's when it really starts to make a difference in the world. And it has. I mean, genetic sequencing and genetic testing and companies like 22andMe are amazing. Or 23andMe.
That's
are-
23.
are amazing.
Did you say 22 of me?
I did say
How funny is it? Because 42,
23 and 40.
the bugs got you.
There's something there, dude. There's some cicadia code in there. So protein. So we can now sequence logically, I suppose you could say, or linearly is a better word. Protein structure. So that means the structure of a protein from start to finish is one long genetic chain of A, C, G, and T, I believe, which is what the 4 different things that can make up our genetic code. And what these proteins allow us to do, they're super fundamental in the building blocks of daily bodily functions. They allow for the internal fighting of bacteria, and
They make up our genes.
They make up our genes, and they're even super important in CRISPR gene editing, which you may have heard of, which is this revolutionary technique of essentially using genetic scissors
Yeah.
to cut out certain parts of our genetic code and paste new, better information in there. And there's even been a Chinese scientist who has used CRISPR to genetically engineer a baby that is still to be born to be hopefully resilient from AIDS.
I think so.
I think so, which is
Super
cool.
controversial.
Yeah, super controversial. He just kind of went at it in his own way. But yeah, proteins and human anatomy and the building blocks of our bodies and our lives are super important.
Yeah, and just to be precise about that, so a protein is just a sequence. So what are the 4 bases? It's adenine, thymine, cytosine, and guanine.
Guanine, yes,
Guanine,
I was
right?
going to say
And-
glutamine, but guanine.
Glutamine. So those are the bases that make up our DNA, and a protein is just some sequence of those. So it could be A, A, T, C, G, and that would be
Exactly.
one protein.
Exactly, except it's not, it's a little bit longer than puppy.
Yeah.
So it's essentially A, C, G, and T for pages and pages and pages and pages in fairly random combinations. And that linear list of information doesn't actually tell us what the protein looks like.
Because it folds up and it makes like a 3D shape.
Exactly, because within each of those lines, A's and C's and G's and T's can interconnect within the 3D shape
Yeah.
of the protein. And the shape of the protein ends up becoming the key for the lock that it's supposed to go in. So different proteins that do different functions will have different shapes.
Yeah.
And before AlphaFold came along, this was pretty much an uncrackable problem. There was this thing called Leventhal's paradox, where with current technology, and by current I mean up to like 2015, 2016, when AlphaFold started tackling this problem, what they would try and do is they would use immense amounts of compute to brute force this.
So I think there was research happening. I think brute force was like the last resort.
Okay.
But as you were saying, it was a crazy paradox where if you tried to brute force for a single protein, like the amount of combinations you'd have to search would take, like the amount of search time would take longer than the universe or something.
Yeah, so basically if you were just to try every possible combination this protein could be in and settle on the definitive one, the amount of time that would take you is more than the amount of time that has existed in the whole universe. And that's with our incredibly fast computational power.
But there was definitely like people weren't brute forcing. They were doing
Okay.
other things. There's like some really good research, but it wasn't as good as what happened.
Well, yeah, it was good, but not good enough because
Yeah.
they couldn't figure it out. And really where this ties into our podcast is that this algorithm, AlphaZero, was able to solve this fairly efficiently and fairly quickly. And it wasn't designed for this. I don't know if you maybe want to speak to how much of a major step that is, that we had
Yeah.
this non-specific algorithm that was able to crack this problem far outside its field with relative ease.
So I will say that I don't think that they just basically copy pasted AlphaZero, right? So I don't think, for example, that AlphaFold used Monte Carlo tree search. I'm not sure, but I think it was just the general principle of using neural networks to predict structures.
Okay.
And it's because the concept of like a tree doesn't really make sense in the context of biology. You would trying to figure out so for example a tree was what's the next sequence to add. As soon as you added that sequence, it's a different protein, right?
Okay.
So
it could be actually an example of where the alpha algorithm was used without its Monte Carlo
Yeah.
capabilities, and it was essentially just using that evaluation protocol.
Yeah, and they definitely use neural networks.
Yes, yeah. It was a generative network. I know that much.
But it was pretty crazy that it was able to do what you did, as you said.
So how did it do it?
So, I mean, just to back up and also just to say why proteins are an important problem.
Yeah.
If you can figure out if you can predict how a protein's 3D shape will look like just from knowing its sequence, it'll help you with a lot of things. So one of the things that can help you is like designing better cures, because you actually understand how the disease or like how the protein in the disease or whatever looks like.
Right.
But it also helps with drug experimentation. It's not so, if you could predict the shapes of drugs, it doesn't cost as much compute to just like run experiments of how this drug will interact with this drug, because actually simulating the drug and what its 3D shape looks like is pretty easy. So that's why it's like super important. It's a super important problem.
Yeah.
But so what was the question? Sorry.
Well, the question was, how does AlphaFold actually interpret and return this data for a result? Okay. So just to getting there, I want to kind of talk about how people did it before AlphaFold did it. So you have this 3D shape, and one way you could try to figure out what the shape looks like is to basically throw things at it. Okay.
Right? So imagine you had a box, right? And you couldn't see it. It was in the dark or something, but they told you that you could throw tennis balls or something at it, right? And you'd throw a ball at it and it would bounce and go somewhere else, right? But you could throw balls at it from any angle. So by trying to see how it reflects and like the different reflection angles, you kind of get a sense for the shape.
Of the shape.
Right?
Got it. Okay.
So they did this for protein molecules.
Okay.
But they used X-rays and they used something called nuclear magnetic resonance. But it was basically throwing stuff at an object that you don't know to try to figure out what its shape is. And it's super hard. In fact, it's so hard that it was first successfully done for hemoglobin.
Okay.
And the guy that figured it out won a Nobel Prize.
Oh, wow.
Yeah.
Okay.
It was really, really tough. So that's the one option, throw things at it, right? The next option you have is to just try and simulate the physics, right? Because the protein, so cytosine and guanine, all of those are just chemicals, right?
Right.
So you could be like, well, I know how molecules act, right? I've got an organic chemistry PhD or something. And you could just try model the interactions between all the molecules and the the intermolecular bonds and try simulate that for the full molecule.
Right.
But it's also super tough.
Yeah.
And it's also like extremely computation intensive, so you can't do that. And so that's why that's why it's such a big field of research, and it's actually why it was quite a big thing when DeepMind did so well.
Well, this is also, we're getting, again, as you will probably have heard from listening, intelligence versus computational power.
Yeah.
You know, the more intelligent we seem to get with our AIs, the more power we need.
Yeah.
But that is a diminishing scale. We eventually run out of power.
Yeah.
And a lot of the sort of woeness that's making the experts in this field take a step back are these clever ways of coming around computational capabilities and doing like AlphaZero used pretty much 1/10 of the power as Stockfish to come to to come to a better solution. AlphaFold is using orders of magnitude less compute to solve this problem that that previously just required unbelievable amounts of compute power.
So it's basically like swapping out compute for data.
It's basically swapping compute for data. Yeah. So this is also another thing. Data sets.
Yeah.
Data sets, essentially how they feed this information into this AI dictates a lot of what it is capable of doing. And do you know how they trained?
Yeah, it's actually super fascinating.
Yeah.
So So you have the sequence that defines a molecule, right? Like a protein molecule. And in a perfect world where like things aren't very tough, you would just feed it all these sequences and then give it the prediction of what the 3D shape was. But it turns out just giving it the sequence was still, there were just way too many possibilities for what the molecule was, right? So I want you to imagine a strip of paper, right? Almost like, remember how we spoke about Turing tapes?
Yeah.
Imagine just a strip of paper, and in each block it has A or T or C. And what the 3D shape is, it's kind of like you take that piece of paper and you scrumple it up. And
You
make like
literally fold it, yeah.
Yeah, you make it. So what they did is that they took advantage of evolution. So what happens to proteins is they mutate sometimes, right? And what happens with some mutations, for example, where there was a T in a specific place, it might be replaced by a G or a C. So imagine you take this piece of paper, you scrumple it up, and then I have some spray paint, and I just spray paint a little corner of the paper, right? So that little area has little black blobs on this white piece of paper. And then I take the paper and then I straighten it out again, right?
Right.
So what you'll see is that most of the paper will be white, but on these certain specific tapes, there will be some black blobs where I spray painted it, right? Now you can go the other way around. So those black blobs represent mutations, right? But now if you started with this flat piece of paper and you were like, oh, look, there are these certain places where
these mutations are
it seems like
seemingly
these mutations
randomly.
occurs. What it means is that by like inspection, if I had to fold it, those black blobs would be very close to each other.
Okay.
Right? And that helps to greatly like simplify the problem, because now you know that like not only is this protein whatever sequence it is, but these black blobs on this tape, when folded up, should be extremely close together.
So basically, instead of getting a data set for saying king moves here, queen moves there, it's getting a data set on what evolution favors.
Yeah, so the data set would be just this sequence of T's and G's and C's, whatever.
But
and
with the
3D
favorable genetic variations.
Yeah, and that's kind of like an extra step to it. So they would like be like, okay, so I know that this protein is that these places in the protein are going to be super close together because they have these genetic markers from evolution.
And that would then be evaluated as a good move. So
it would just help you. So it will just help you know that like whatever the 3D shape is, these places where there's like the black blobs on the tape should be close to each other. So it might be all types of different shapes, but no matter what the shape is, you've greatly simplified the configurations because you know that these places have to be close to each other.
Mutations are the drivers, and very interesting, dude. Very interesting. So that, just on a total side note, that could be used to simulate evolutionary environments. You know, they could start with a single cell and favor mutation and see where that.
I mean, that sound. I don't know much about biology, but that would be amazing if they could do that.
Yeah, I mean, you know, you got to think about what's next for these people, because 2019 has been quite a big year for these discoveries.
Yep.
We've beat a lot of stuff we thought was unbeatable. We've reached a lot of milestones. So now these next milestones aren't quite as notable as beating someone in chess or checkers or whatever.
Yeah.
But the idea of being able to do something like a cell simulation with evolutionary mutation is amazing.
It's incredible. It will change so many things.
As far as solving the universe goes, you could, in essence, put the data set for physics in there. And potentially simulate. I don't know if you would even say
law or whatever.
I don't even know if I should say simulate a mini universe, but like
I think we're still very, very, very,
very, very far away from that. But last year we thought we were very far away from protein folding.
This is true. But just to keep going, so you have this data set, and then you also have these little hints from evolution that helps you figure out where things are close together. And what researchers traditionally did is that they were like, okay, I know that these two places should be super close to each other. So imagine we said if two places should be close together, make that 1, otherwise make that 0. Right?
Okay.
So it's kind of like a binary option for where things should be close to each other in this 3D space, right? So almost after I scrunched up the paper, this tape, I know that like these two parts should be close together. What DeepMind did is that instead of just saying, oh, okay, let's make this 1 or a 0 to represent if they're close to each other, they just modeled all the distribution of all the distances between all the different parts of the molecule.
Oh,
And that
okay.
led to much better results.
Okay, so they modeled the distances between all the different parts.
Yeah,
And fed that into the data set
into the neural network.
into the neural network with the favored genetic mutations, and that was
Yeah.
a major step in efficiency, really.
So I think and it's interesting because when the researchers looked at what DeepMind did, they were terrified, right? Because it's fascinating. So I was reading an academic that wrote about this, that participated. And he said that once they found out that DeepMind, we haven't spoken about how big the victory was. You want to maybe first talk about how well they did at this competition?
No, you, please,
Sure.
please.
So it was a competition, but the name of the competition was, I think it was like CASP.
Okay.
But the whole point of this competition was they would give you a random data set with these proteins, right, with these sequences, and then you'd have to predict what shape you thought it was. And they knew what the shape was already. So everyone would give in their shapes, and then they'll be like, okay, well, you got 2 right, you got 3 right, you got 10 right. DeepMind, I think out of I forgot what the total number of proteins was. I don't know if it was 100, but they got 25 right.
Oh, okay.
The people who came in second got 3 right.
Sure.
And these are people who spent their whole lives in academia, tenure. This was their job.
This is another major thing, is that the people who got 3 right have spent their lives trying to figure out how to crack this problem, whereas DeepMind has tried to crack the problem of thought and intelligence.
Yeah, and it took them 3 months.
It took them 3 months, and they moved further along just by cleverly simulating intelligence and thought.
What makes it even worse is that most of them had no biology
Experience.
expertise.
Yeah.
They were all
I've
machine
heard the vibes between biologists.
Yeah, it was. In fact, one biologist basically said that the amount of improvement so every year there will be some improvement in the field, right?
Right.
He said that the improvement that DeepMind made was approximately 1.8 meetups or competitions worth of improvement.
So nearly 2 years worth.
Well, the competition's held every 2 years, so it's almost
4 years.
Yep.
Okay. Well, I think we have pretty extensively covered AlphaFold.
Yep.
And it is not the end of Alpha's journey into intelligence. The next one is one I've been waiting for a long time. We are going to be discussing AlphaStar, the latest offering from DeepMind, and how AlphaStar was able to beat the world's pros at StarCraft, an imperfect logic game.
Are you a StarCraft player?
I have played StarCraft and I suck.
I suck more than you suck. My nickname was Level 1 Bot.
Level 1. Okay. I elevated myself slightly higher than that, but
Hey, it is what
you know
it
what?
is.
It doesn't really matter anymore because the best humans in the world are invalid now. So
That's one way of saying it.
yeah. So if you want to find out how and why this algorithm that was made for Go has now folded proteins and is beating players at real-time strategy games, please tune in to the next episode. Thank you, Pubby. Thank you, Blended. Thank you, Blended Podcasts and Blended Audio. It's a pleasure, as always.